set of asynchronous processing. The functionality the cache manager delivers is on this slide. The cache manager is able to cache pages of open files or previously open files. Even after a user closes a file, all handles go away to file. The cache manager still keeps pages around. It does automatic asynchronous read ahead, so it tries to figure out if the application that's reading a file, if it's reading it sequentially, then it decides that read ahead for that file might be appropriate, and it posts read ahead asynchronously from the application. And if the application uses a sequential scan hint, then it more aggressively posts read ahead. It also does, by default, all writing to files is done lazily, so when an application calls write file to write a range of bytes to a file, then the cache manager simply quickly copies that into the cache and returns to the user program, and the data gets written out later. The cache manager ensures that the data eventually makes it out to disk, and so of course this is a lot like Unix systems have always worked. It supports fast I/O, which Gary's already talked to you a bit about, and I'll be showing you some slides on fast I/O, talking about it some more. You'll probably hear some more about it tomorrow, but the design of the cache manager is one of the main things that really enables us to do the fast I/O paths for read and write. And finally, it supports simple but powerful access methods to access data in the cache. So there's 3 types of access methods we'll be discussing that apply to, in theory, any file that's in the cache. So who uses the cache manager? Well, currently there are, in fact, already with version 1 of NT, all of the disk file systems, NTFS, FAT, and NTFS, use the cache manager. The CD-ROM file system uses the cache manager. The Windows NT file server, already in the first version, uses the cache manager, and also the redirectors. So our network client code also uses the cache manager. So the cache manager truly is a global system component. There's just one cache manager in the system, and he really for all of these sources currently. And standard in NT, of course, an installable file system would be able to use cache manager as well. That's what we're here for, I guess. What can be cached? Well, of course, user data files are cached. As the user reads files, he benefits from caching and read ahead and write behind him. And also file system metadata may be cached. And so if a file system can organize its own file structures, directories, file tables, whatever, if it can organize these data structures into streams, then it can also be cached. And someone asked me maybe something about streams too. Do people already understand streams, or what? Stream is simply, certainly in my talk, a stream is any stream of user data or file system data. It's simply a stream of data that's organized like a file, and you can access it from byte 0 to byte n, where ends the size of the file. So that's what a stream is. So some file systems probably weren't designed to really organize their metadata into streams, and I know, for example, HPFS wasn't designed that way. But if the file system can somehow make that metadata look like a stream, then it can call the cache manager and say, hey, look, here's a stream of mine. Anytime you access a particular range of files, I'll promise to always go to the same place on disk and bring those back in again. And so you can cache your metadata. Now, at this point, I wanted a little digression and just sort of explain how the Windows NT cache manager is actually quite a bit different from, I think, most cache managers that you're probably used to. And I think it might be instructive to start telling you really how ours works. One example of, I basically, when I think about this comparison, I divide cache managers into what I call virtual block cache managers, which is what NT is doing, or logical block cache managers, where Smart Drive is one example of that. OS2 is another example. Novell uses logical block caching, etc. So it's much more common to see logical block caches. So this is a very, very high-level slide that gives a very simplified view of the difference. For a logical block cache, what happens is the user wants to read a range of bytes from the file, which he specifies by a file offset and length. And that read request then will be serviced by the file system. So the file system has to look at this read request and break that down into where those bytes are actually stored on the disk. And a particular range of bytes that a user wants to read may be contiguous on the disk. It may all be in one contiguous spot in the disk, or it may be broken up across multiple runs on the disk. And so the file system has to first take the request and say, well, this is where it is on disk, or this is where the various pieces are on the disk. And then at that point, the file system more or less expects a disk driver. Well, so for example, in the case of smart drive, instead the file system is really calling this smart driver that's implementing data caching, and it takes the physical disk address, or the logical address is the way we have it on this slide, and he looks to see if he has that data in his cache. And if he has the data in his cache, you get a cache hit, and the answer is much quicker. And if it's a miss, he may choose to read that data into the cache off the physical disk and then give you the data out of the cache. Well, NT is different. We do a virtual block cache. So the cache manager actually knows about files, or more precisely, streams. And any stream can be cached. So when a user request comes in to read a range of bytes from a file in Windows NT, we can essentially give that request directly to the cache manager. And the cache manager then says, well, okay, this is a file that I'm caching. I'll go see if I have that range of bytes in the cache, and if I do, I'll give it to you. And so what happens is we've eliminated one translation step. We don't have to first translate the range of bytes that the user wants into some physical address on the disk and then go consult the cache to see if the data is there. We simply can look directly in the cache and say, I want to see if this file data is in the cache, because I've organized my cache by file streams. So one really interesting thing that we note here is if you look at real carefully at that last bullet, the file system's not involved at all, and that's really the secret to our fast I/O path. We don't need file system at all to service a read request to a cached file, and we'll talk more about that later. In addition to being a virtual block cache, one thing that I should also point out at this point is that the NT cache manager, the way it works is it maps streams. It maps them by calling memory management, sections, and maps views into these files, and it faults pages to memory. So really it's a map file model, and we're going to look at really how all the mechanics of that work. But it's important to note that we're using this virtual memory model, and therefore, in total, looking at the NT caching system and comparing to a logical block cache, I see lots of advantages. Of course, I would, but these are the advantages I find, and they are there's one single memory manager in the system. I don't have to say, well, I want to make my data cache 4 megabytes, and I want to leave the rest of it for images in the system. Everything's dynamic. The data files compete with images and page pool and the pageable portion of the executive, and everything is considered equivalent and compete. So 1 minute, in theory, you may have on a 16 meg system, you could maybe have as much as 12 megabytes of cached file data in memory, and the next minute you start up Seafront or something like that, and he is a rather large program and starts taking a lot of page faults, so he'll push data file pages out of the cache, and now the next minute you may have 8 megabytes of image pages and 8 megabytes of data cache. So it gives you kind of an idea of how dynamic this is. And it's all managed by one single central component, and that's memory management. And Lou will talk to you about Memory Manager tomorrow. Another advantage is that we automatically get cache coherency between certainly cached file access and memory mappers of files. And that's because when a user maps a file and references a page of that file through whatever virtual address he's mapped it to, he actually is accessing the very same physical page that the cache manager is also accessing when it's reading or writing to that file through the cache. So you automatically get cache coherency. I didn't say synchronization. That's another story. You know, you still have to use file lock or whatever to synchronize, but you do automatically get coherent access between mappers of files and cached file access. Another advantage is that we can do precise read-ahead. I don't know if most disk cachers attempt to do read-ahead or not. I guess you could see that your pattern access was going along sequentially on disk and hope that you're not going to read the next physical addresses into your cache, and at the same time the file system does a segue off to another part of the disk. Anyway, we don't have that problem with a virtual block cache, because what we are caching is file system data. So even if the file is all jumbled up into lots of tiny pieces, we can still, when we do read ahead, we're drawing all those pieces into memory, and we will, if we detect sequential file access, we can guarantee that the next pages of the file will exactly be in memory, so we can do precise read ahead. I think a lot of disk caches will do lazy writing. However, one additional feature that we get that we'll be discussing later with the virtual cache model is that the cache manager can keep the file system up to date on just where he's at in the file. So if a file system is trying to be too secure and maintain a high watermark beyond which even in the event of a system crash, he'll never let anyone read beyond that point in the file for security reasons, then he can do that because the cache manager is always calling back and saying, oh, by the way, I want to let you know that I've already written first 1.7 megabytes of the file, and you can consider that valid. And a little later he comes back and says, well, now I've written the first megabytes of this file. And finally, the virtual cache model that we have enables the fast I/O mechanism in Windows NT. And I did think of a couple other reasons. You know, we also, since we're not strictly a disk cache, we're able to cache network redirectors. And also there's things like if you delete a file on NT, because the cache is file oriented, we call memory management and say, hey, someone deleted this file, you may as well throw all of its pages on cache and put those pages to better use. So we see that a lot of advantages of going with this particular caching model. So here's a block diagram of the interaction and all the components that are relevant to understanding how file systems and the cache manager and memory management all work. So you see all these components on this picture. There's the cache manager and the virtual memory manager in the lower left-hand corner is actually maintaining the cache streams. And the IFS driver there in Windows NT, that could be any of the drivers I mentioned, the 3 disk file systems, the CD-ROM file system, or the redirector. The network file server doesn't really fit in that same spot in this picture. He looks more like some component coming in from the top. Looks more like an application the way he accesses cache. But, and indeed, any installable file system would fit in that particular position in this picture. Finally, you see the IFS driver talking to the fault-tolerant driver. And that's really just called out here as a possibility to let you know that the file system has no idea whether he's talking to the fault-tolerant driver or whether he's talking directly to just some simple disk driver, and he doesn't have to know. And so, in fact, from here on out, I'll just refer to the disk driver, and I won't speak any further about talking to the fault-tolerant driver because the file system can handle that completely transparently. For those of you who don't know for sure what the fault-tolerant driver does, it delivers mirroring, mirror disks, and thriving both RAID level 0 and 5 and 4, I think. I don't know, but it's thriving with and without parity. Now, if you look a little closer at the arrows in this picture, you see sort of at least one circle going on here, and that is if a request comes into the file system may go out and call the cache manager, and the cache manager then could take a page fault, which will call memory management, and that's right back to the file system. So, An immediate question might be, how do I keep this request from just circling there forever, not coming back? And to understand that, I want to just briefly say, I should have a slide about this, but I just want to briefly say that the read and write paths of a file system are really, there's two separate paths typically in the read and the write support in the file system, and that is a non-cached path and a cached path. So every read request that comes to the file system in the form of an IRP, there is one flag in the IRP flags field which is called IRP under no cache, and if that flag is set, then that indicates to the file system that he's really supposed to go to disk this time, regardless of, never mind if this particular file is being cached or not. The file system shouldn't have to worry about that. But if the IRP no cache flag is set, then we're really supposed to go to disk this time. And if the IRP no cache is not set, then that says we're trying to access this file through the cache, and that causes the file system to call the cache manager. So this stuff should become a little clearer if I make some examples. If we, for example, first let's just talk about simple file reads. If a user issues a read to an open file that it's open by default for being cached, then the first read comes directly to the file system in an I/O request, and the file system now, actually on the first read, it has to call the cache manager to tell it that it wants to start caching that file, and we'll take a quick look at that call later. But essentially, on the very first read call, a file system has to really get initialized with the cache manager, and then it calls the cache manager to say, I want to read this range of bytes. Now, if that data is in the cache, then the cache manager will return that data directly to the file system, and that cache hit, the file system returns back to the I/O system and back to the user, and that's the cache hit is as simple as that. On subsequent reads, if I take the fast read case as the next example, once a file is cached, then the fast path is enabled, and in fast path, a read request comes into the I/O system, into NT read file, and NT read file has what we call the cache manager directly. He says, I know this file is cached. Can you handle this read directly? And again, now if the cache manager gets a cache hit, then he returns immediately with the data, and we return from NT read file, and we never once talk to the file system. And in fact, we've for a small read, we've measured that path. Don't hold me to any numbers in this presentation, but the last time I was doing casing and stuff, that path was on the order of just a little over 300 instructions on an Intel machine. So it's real fast. I mean, we get the data back to the caller very quickly. Now, if the data is not in the cache, it's a little more complicated. Say the first read comes into the IFS driver, and the IFS driver says this is to a cache file, so he goes off and calls the cache manager. The cache manager doesn't actually try to ask itself, is this data in the cache? It simply maps the data. If it hasn't already got it mapped, and it tries to copy the data back immediately to the caller's buffer. And in this example, if the data is not in the cache, then the cache manager takes the fault to the virtual memory manager, because the page isn't valid, and the memory management takes the virtual address. He finds what section this is, page fault has occurred in. He finds the file for that section and ends up issuing a read request with this is a second IRP now. He will issue a read request back to the IFS driver to say, please do this non-cached read for me. So now, when this IRP comes in, the file system sees the flag that it's a non-cached transfer, and now he really goes off the disk, and he'll hand that request off to the disk, and we wait for the data to come in. And when that disk request completes successfully, then the IFS driver will return to memory management. Memory management says, great, we successfully brought that page of data into memory. I will make the page valid now. Returns to the cache manager, and the cache manager can proceed to copy the data into the caller's buffer, and then the cache manager returns to the file system, and on back up it goes. So that's really sort of the scheme of things. Does everyone understand that at this point before I go on, or is that part of it pretty clear? Or? I've probably already sort of covered first bullet or two of this slide. Basically, we've been looking at that diagram, and you might want to remember where the diagram's at and refer back to it later in the talk. But we've talked about how we're using a cache or a map stream model, and what the cache manager really does, he maps these streams with fixed size views. And another number that's just, I don't want to commit to forever, but the current view size that the cache manager used in version 1 of the system and also in Daytona is 256 kilobytes, which is also a quarter megabyte. And so he takes a very simple approach. He maps one view to the first 256K of the file, another view the second 256K of the file, another view third 256K of the file on demand. Of course, he only maps portions of the file as they're accessed. And he has to manage these views in the background. I don't think I have a slide on that, but there is some limit to the number of views he has. So some view of a file that hasn't been used for quite some time, the cache manager will come along later and finally unmap those views. Or when a user closes the last handle to a file, then the cache manager receives a call which will cause him to unmap the whole file at that time. And the pages, when the files are unmapped, the pages are still remembered. We still know where all the pages of the file are in memory. They're just none of them have valid virtual addresses at the current time. So they get to stay in memory as long as they can until we need those pages for some other purpose. And so if somebody comes back a few seconds later and accesses the same file, chances are and it's a relatively small file, chances are they'll get file hits all over again. Hopefully you've all seen this blinding speed by using NT. So the model's real simple. We just once we map these pages with these fixed size views, we fault pages into memory that people want to read, and we modify the pages in memory, right in place in memory, and then the cache manager makes sure that any modified pages eventually get written out to disk, and he uses delays. He just uses periodic delays until, provided there's lots of available memory. And so he will, on the average, perhaps write data out 4 to 5 seconds after it was modified. And of course, at the same page, if an application is doing very small writes to a file page, then he can consolidate 10, 20, 30, however many writes at once before he ever actually has to write that page a single time to disk. There's a question back here.
Is there an age interval for the cache manager to flush things out to disk? I bring a file in, I'm looking at it, and I don't look at it anymore, but I've modified it. Is there some interval you use by default?
Right. The question is there some age interval that determines how we write that data out to disk? And there is. I can tell you the current numbers. They're subject to change, but right now the cache manager wakes up about once the approximate algorithm right now is very simple. The cache manager wakes up about once a second and attempts to write about 1/4 of the dirty data that he sees at that time. And the next second there may be more or less dirty data, but that's approximately what he does. So, and he does use a round-robin algorithm so that it's not possible that some data will get unlucky and stay dirty for a very long period of time. So in general, most file data will get written out in like 4 or 5 seconds. There's a couple other questions.
The fast I/O, is that new for 3.5?
The question is fast I/O new in 3.5? And the answer is no. That was already in version 1 of NT. I'll take one question.
Is it possible to bypass the gathering like database file system so that
Right.
admit that you know that data will count out without that?
Okay. The question is it possible to bypass the cache manager for purposes like a database or whatever? And there's sort of two answers to that, and we'll see some of this later. But firstly, yes, you can. A user can open a file and say, look, I just want to cache this file at all. And that's, I suppose, typically what a database is going to do. I don't want to cache this file at all. Or a user can open a file and say, I want this file always written through. So when I do a write, I want it written through to disk before you return to me. So there's that possibility. And finally, this is all on a later slide, but you can also explicitly flush a stream. So, okay. And MM manages global memory policy, and we're gonna look at that right here. I've explained how the cache manager accesses files by just mapping them and following the pages into memory. It's now interesting to think about, well, where does he map those files? In fact, there's memory management implements some functionality in the system which is called the system cache. And that is what the cache manager uses exclusively. So this describes the attributes of the system cache. It varies in size. On the smallest system, like an 8 meg system, the system cache has only 64 megabytes of virtual address space dedicated to it. So the cache manager has to live within that space, and that's actually not too bad because 64 megabytes gives him 256 views. And on a large system, especially a large server system, would go right up to 512 megabytes or half a gigabyte of virtual address space, which will be dedicated to the system cache. The system cache is visible in all kernel mode contexts. This is very important. We actually did some experimenting way early on where we sometimes had to, we mapped files to a process, and therefore every cache hit involved a context switch. We couldn't get at the cache data without doing a context switch, and that was a disaster for performance, of course, and we quickly realized we needed to have a capability to map files right into kernel mode. So the system cache is visible in all kernel mode contexts and really at any priority. However, you're not allowed to take page faults above priority 1. It competes. The system cache has its own working set. So just like all processes in the system have a working set, the system cache also has its own working set. So in a sense, you can think of the system cache sort of a special process in the system that has its own working set. And Lou will be making a presentation tomorrow. I believe he'll tell you that actually the pageable portion of the kernel also shares the same working set. And so since the system cache has a working set, it really just competes for physical memory right along with all these other guys in the system, which is all the images, any applications running, the pageable portion of the kernel, any user map file sections, page pool, just competes along with that. And so I gave an example earlier where in theory and in reality, the utilization of physical memory can flow quite dynamically from images to page pool to cache files, and it flows quite nicely, and we put all the policy, all the decision making on who should get physical memory in one place, and that's in the memory manager. So that's a big advantage. Okay, so now we'll start talking about some interfaces. The bird's eye view of how you talk to a cache manager is on this slide. Essentially, to initiate caching on a file object, and again, file objects just represent a stream. So to initiate caching on a stream, you call a routine CC initialize cache map. And if that routine completes successfully, then you now have this file cached, and you can now use any of these access methods that we'll be talking about, or call a variety of maintenance functions on that cache stream. And then when you're all done using this particular cache stream, then you can call CC uninitialize cache map to say, okay, I don't need that stream cache anymore. Now, if a file is open for shared access, so there's actually, say, 3 or 4 users using the same file, these CC initialize cache map and CC initialize cache map are performed on each caller's file object. So if 4 processes are accessing the same file, then it's cached 4 times. Of course, the file pages are only present once cached, but there's 4 people now saying that they want to use this file in a cached method, and that file will remain actively cached until the last person closes his handle. So now we're going to look at some access methods. The copy method, I guess, couldn't be much simpler. And this is far and away the most common method of accessing cache for your files. And to read a file, you call CC copy read, and you say, well, here's my file object, here's file offset and byte count that I want to read out of the file, and here's the buffer I want you to copy that data into, and that's all you have to do. So on return from that call, the data is written to the buffer. And you do get a byte count back, so that if you happen to hit end of file, you'll see a reduced byte count. CC copy write is the function that writes data into the cache, and it's just basically the same interface. You say, well, here's my cache file object, here's a byte file offset and byte count of range of bytes that I want to write in the file. Here's the buffer that contains those bytes, and the cache manager now will copy your buffer into the cache and mark that infected page as dirty, so that they ultimately get written by the lazy writer. And that's really it. Now, of course, the background of the cache manager, it's not quite that simple. The cache manager, the cache manager has to first verify that the file's cached, see if he already has a view mapped to the range of the file that you want. If your request happens to span one of his view boundaries, and he has to break the request up, map one view, copy some of the data, map another view, copy the rest, etc. So there's a lot of details, but the user interface is really as simple as this. All local file I/O on the system, and all redirector I/O, and all I/O to the CD-ROM file system locally. All of those go through these methods, and that's it. That's it's quite simple.
Doing a write to a file, the page already exists a file, but it's not present in virtual memory. You're going to go through your cache manager, and that's going to cause the page fault. Is there some logic down there so that you don't cause the page to be written if you're going to overwrite the whole content of the page, avoid the page in?
Right, I get the question. Yeah, that's a good question. If I'm writing a file, I may even be just producing a file. So if I call CC copy write, of course, first level approximation, what we'd say is, well, first we have to fault the page into memory in order to copy bytes into it and write it back to disk. That theoretically, that's what we're doing. However, we do in fact avoid reading the disk if we see that the pages, there is no valid data. Well, there's two cases. And I don't have this on a slide, so yeah, I may explain this right now. If we see that one whole page or some integral pages are being completely overwritten, then it doesn't matter what the state of those pages are on the disk. We'll just materialize those pages, and we'll just materialize pages of uninitialized data in memory and materialize them into the section and copy into them. So we avoid the disk read in that case. Also, we have a concept which I'll be talking about later, which is called valid data length. And if we go to fault a page that is beyond valid data length, which means this is a page in the file which has never ever been written, then also in that case, even if you're going to go write 10 bytes into such a page, we will suppress the disk read in that case. So we really only fault pages into the cache in order to write into them in those cases where we really have to get some existing data off the disk. Okay, the second access method isn't that much more complicated. It's called the MDL method, or really what it's for is for DMA. The MDL method is used exclusively by file servers right now, and it gives the file servers the ability to do DMA directly into and out of the cache. So, for example, in the extreme case, I don't know how far they're always willing or always able to take it, but in the extreme case, you have a DMA network device, and you can organize a raw read coming into physical memory. You could in theory come right off the wire into pages in the cache by using this method, and to write that would be an MDL write, and an MDL read would do the reverse, read data directly out of the cache onto the wire.
What's MDL?
MDL stands for memory descriptor list, and it's a term that some of you probably have seen that if you've done device driver courses or something, but a MDL is a memory descriptor list, and it consists of, there's a header with some information, followed by all the physical page frame numbers which constitute that transfer. So maybe I can explain that a little bit by example when I talk about CCMDL read. If a server wants to honor a read request to some client on the network somewhere and wants to do this through the cache, then he would issue a CCMDL read and say, here's the byte range that I want to deliver to this user. And the cache manager now will go make sure all those pages are resident in memory and create this memory descript list. And so, for example, if I wanted to read, 5,000 bytes of the file starting at offset 4,000, then that's going to cover, I pick bad numbers, that's going to cover probably 3 different pages. And so the cache manager will go bring all those pages into memory, and he will create an MDL which says, okay, my offset into the first page is 4,000, and the byte length for this transfer is 5,000, and here's the 3 physical page frame numbers, one after another, that describe where those pages are in physical memory. So the MDL just really tells the server where the pages are in physical memory. So if he has a device that DMAs to physical memory, then that's all we need. We can do a DMA transfer of that data out of memory. Or if the server is talking to a dumber device that has to physically move the bytes and calculate CRCs or whatever, then he can take that MDL, which only describes physical addresses, and he can map that MDL and get real address that he can access even at interrupt level to copy that data off to his buffers. So it's basically just this method to give the server very, very high volume access directly into and out of the cache, since the server is a trusted kernel mode component. Now, when the server does a CCMDL read, of course, the cache manager makes these pages available, and he actually also locks those pages in memory, so they can't leave memory once the cache manager has completed an MDL read. And so the server now will take the data out of the cache and go put it on the network. When he's done, he is supposed to come back and call the cache manager. He has to tell the cache manager when he's done with those pages. So he calls CCMDL read complete, and then the cache manager knows, aha, I can go unlock those pages and just, I leave them in the cache and let them float with the rest of the cache. But the server has to say when he's done reading the data. And similarly, on CC prepare MDL write, the server says, geez, I have this big transfer that I would like to write into the cache off the network. Could you please prepare those pages for me to write into? And again, like the question I had earlier, if possible, if there's whole pages being overwritten or there's some data being written beyond valid data length, then we don't have to read the disk again for the server. We just go materialize pages in memory. We do one thing different for the file server than we do for local file systems. In a local file system case, when we decide to suppress a disk read, we know, the buffer's right there, and all we got to do is copy the data into the cache, so we can use uninitialized pages of the file, and we know that we'll get the data in there. On the other hand, for the file server, we do free zero the range of bytes that he requests. So he says, I want to write this range of data into the cache. And most of the time he does, but once in a while, if a virtual circuit goes down, something like that, and the write doesn't complete, we don't make him come back and say, well, I didn't really do that right, or I only wrote this many bytes or whatever. He just tells us when he's done, and it's his responsibility to go back to the client and say what happened. But he just tells us when we're done, and we unlock all the pages and mark them dirty, and so that they eventually go out to the file. Now, so if that MDL write didn't complete, we'll end up writing the file where he had intended to write. Called C2 security again. Okay, now the third and final access method is called the mapping or pinning method, and this method is really used exclusively by real file systems, i.e. the disk file systems and NTFS. It's not used by redirectors or servers currently. And this method allows these programs to say, again, it's like they want to access the data directly in the cache, but they just want a virtual address. They want you to say, well, please make this range of my stream resident for me so that I can go manipulate it, or just, if I'm doing a direct enumeration, I might say, I want to map this page to my directory stream so I can go get some file name information and give it out in the directory query. And so this just gives file systems a way to access their metadata without having to do any data copying. So CC map data, for example, then gives the file system the ability to say, well, here's my cache file object. Could you please map this range of the file, this file offset and byte count, map this range of the file and give me a single virtual address back at which I can just go reach out and touch the bytes. And so he gets that virtual address back in a handle, which he's also supposed to use in the final call on this slide to say when he's done using that data we've mapped for him. CC pin read is very similar to CC map data, except that particular routine is meant for when the file system wants to perform read-write access on some part of its metadata. So this routine costs a little more overhead in the cache manager because now he allocates a data structure, a buffer control block to describe the data that he's back to you. And you can now, if you want, not only read those bytes of data directly in the cache, but you can modify bytes of data directly in the cache also. And then you must tell the cache manager that you've done so by calling cset dirty pin data. I should point up here. I'm looking down here. But you should call set dirty pin data to say, I modified that data you gave me in the cache. And then the cache manager will see that eventually gets written out. CC prepare pin write is just another slight variation where a file system may say, well, I just want to write some range of the file for the first time. So, in the event that I'm asking for a whole page, please, don't read it from disk. Just prepare a page in memory for me, and I'll write data into it. And by the way, I'm not going to tell you it's dirty either because I told you I was going to write it in the first place. So, pin map data is a service where I best make an example with, like, if you're implementing something like a B tree for a directory, a file system might want to do a create, so he wants to add something into a B tree, and he has to walk the B tree, which may have 2 or 3 or 4 levels or something. So he would use CC map data to map portions of the B tree as he walks down the B tree and finds whatever he's looking for. And then when he finally perhaps gets to the bottom of the B tree and has found some spot where he wishes to insert or delete something, then he might turn around and say, okay, now I've CC pin map data. I've previously mapped this particular buffer. Now I want you to pin it for me because this is in fact the one I want to change. So he gets fast access as he walks down his B tree, and then when he gets to the bottom and finally decides what he wants to modify, he just pays to the additional overhead for write access on that one buffer by calling CC pin map data. So kind of alluded to these other two services. CC set dirty pin data is the routine that a file system should call to say, I've modified this buffer that you pinned for me. And CC unpin data is actually paired to the first 3 bullets on this slide, or the first 4, I should say. When you've gotten some data into memory by either of those first 4 calls, when you're done using that data, you call CC unpin data to tell the cache manager you're done using it, so that he can let that page loose. So that is the method. There's a few maintenance functions. Some of these are optional, some of them are more or less mandatory. To start with, there's CC set read ahead granularity. When you first start caching a file, by default, what the read ahead unit is for that file is 4 kilobytes. That's an unfortunate, I wish we'd picked it the other way around, but right now it's the default is 4 kilobytes, and so what all of our current file systems do is they, right after every time they cache a file, they turn around and they say, oh, and by the way, please set the read-ahead granularity for this file to be 64 kilobytes is the number we use now. And 64 kilobytes happens, there's a symbol in one of the header files, which is maximum disk IO or something like that. And so that's the, even if you tried to read more than that at once, MM would break it up anyway. So typically the file systems say, well, that's a pretty good number, and they settle for that number. And so all of our current file systems all switch to 64 kilobyte read ahead. And similarly, CC set dirty page threshold. This is used actually very infrequently. I'm going to talk a little bit about what happens when we accumulate too much dirty data in the cache. We have to start throttling things in. And CC set dirty page threshold is intended for file systems which have very slow devices, like, for example, the redirector on a slow comlink, 2400 baud link or something. You might say, well, look, there's no point in me at processor speed filling up all of memory with dirty data when I can only dribble it out at 2400 baud. So he says, please give me, I think in extreme cases he'll say to only give him 1 or 2 pages of dirty data at one time. And at that point we always make him wait until we've written that data before we let him dirty more pages. So for the most part you can forget about this service, but if you do have a very slow device and you want to be kind of a good citizen and not build up too much dirty data, then you would set the dirty page threshold to some low number just to limit yourself. And I'll show you how this is keys into write throttling, which is I'll be presenting in a little bit. CC set file sizes keeps the cache manager aware of any changes to allocation size, file size, or valid data length. He needs to know about those changes, and I'll tell you what the rules are for calling this routine. CC flush cache is a routine that will explicitly flush dirty data in the cache at the point of the routine being called. So when you call this routine and it returns to you, it guarantees that byte range you specified has been flushed through the disk. So this is used, some file systems may use it as, I don't know, part of their data integrity, or they may also use it to support the NT-flush buffers, flush file buffers call, which is an API call that a user program can use when he says, if the user program says NT-flush buffers file, the file system has to turn around and call the cache manager and say, CC flush cache, please flush the stream. So CC flush cache does take a byte range, or if you don't specify a byte range, it flushes the whole stream. CC purge cache section is a routine that throws data out of the cache. People always, we have a particular terminology. I know some people probably use flush and purge different ways, so please be aware of the way we're using them in the cache manager. Purge says I don't care whether the page is dirty or not, just throw it out of the cache because I guarantee I'll never need that page anymore. And so, for example, if a file's been deleted, you would call CC purge cache section to have all the pages thrown out of the cache because the file's been deleted. And finally, CC zero data is just kind of a service that the cache manager provides again, if you're a C2 certifiable file system and the user first writes maybe up to 10,000 bytes in the file, and then all of a sudden jumps to 1 megabyte or something and writes some more data out there, now you have a problem with the data in between. And so CC0 data will allow you to specify specify a range of the file that you wish to have zeroed so that nobody can come back later and read some uninitialized data from that range of the file. And the cache manager then will try and do that in the most efficient way possible. And in particular, he'll go up to some threshold that he's willing to zero write in memory, so he'll materialize a whole bunch of pages in the file and make sure they're zeroed. But if you try a really large range, he might actually start writing directly through the disk, zero that range of the file. Okay, now we're going to start. That's really the. I wish I'd looked at the header files that you guys are receiving. The list of API that I've just presented on these slides are really the the ones that I believe are a complete set and the only ones that we really recommend you're using for the cash manager. There are a few sort of legacy routines floating around that for ideas of the past that still kind of have to be there, but are not recommended. So that's like the full set of APIs that we recommend. So it's a relatively small set, yes, and interface is actually fairly simple.
How do you find out about the roll call list?
Pardon me?
How do you find out about the polling calls for this?
Well, refer back to these slides. I hope I haven't made a cockpit error, but I mean we that was a complete set that we recommend, and so I don't know. I guess I'll leave it at that. So, okay. Someone asked before about, well, does everything always get lazy written? The answer is no. The user has two options. He can call. He can say, I want to open this right through, and in which case the cache manager actually can look at a flag in the file object and automatically write through for you. So every call that you make on to either copyright or the MDL write, on return, those updates are always written through automatically. And then NT buffers file is the NT API that says that somebody wants to actually flush a file, and the file system would support that by calling CC flush cache. Right throttling. Maybe they're giving me signs and stuff. Maybe I'll try and finish the rest of the slides, and if you could remember your questions till the end, I'd appreciate it, I guess. Right throttling. Actually, initially, shortly before version 1 of NT shipped, it was kind of a free-for-all. When users tried to write files, we'd just keep modifying those pages as fast as we could, and occasionally we'd get into cases where we'd run out of memory because we couldn't write the pages fast enough, or we'd sometimes you'd get unlucky and even get a bug check related to that. So we realized that it's a very good idea to throttle writes, and actually even more over like when the server's talking to DOS clients, the server takes too long to honor a write, the DOS client may time out, stop talking to us, and so we really don't like to see that happen. So there's this write throttling capability in NT, and well, here's two routines I didn't mention in the other list. So what can I say? You should use these. CC can I write is a routine that you can call to say, gee, I'd like to write this many bytes into a file. Is that okay right now to write? And you can tell the cache manager whether you want to wait until it is okay, or whether you just wanted to come back and say immediately, no, it's not okay. And so if you tell him you want to wait, then he returns to you. Then you can proceed and write those bytes into the cache. If you told him, well, I don't want to wait, and he comes back and says, well, you can't write that data now, then the file system can turn around and call CC defer write, which is allows him to post a request to be keyed back to him later when it is now okay to do the write. So that way you don't have to tie up the caller's thread or anything. We just kind of have the IO request packet off in a queue and give it back to the file system when it's okay to do that right. Valid data length and file size consideration. The file systems, it's actually in the common FSRTL header that I think if Gary's not already shown that, I know David will be talking about tomorrow. There's 3 file sizes in the common header, and they are the allocation size, which says how much space is actually allocated for the file size, which is the current end of file as far as the user knows in this file, and finally valid data length, which says, well, how far have we actually written data into this file. And the valid data length that's in the FSRTL header actually says how far we've written pages in the cache, independent of whether that data's gotten out to the disk yet. And we'll talk about another case where we worry about when it actually has gotten out to disk. But in general, the rules are written here. Now some of these numbers, of course, are going to change at the same time. You really only have to call CC set file sizes once, but the rules for ultimately calling CC set file sizes are: if the allocation size grows, you better call CC set file sizes. If the file size changes at all, you need to call CC set file sizes. And if the valid data length shrinks, you need to call the cache manager. And it's very important to follow those rules, because if you don't follow those rules, some bad things may happen. I mean, the user may read beyond file size, for example, or else you may stop getting notified. If you've truncated a file and didn't tell us that valid data length shrank, then we won't tell you when we rewrite that range of files, so that you can allow that data to be visible again. And the cache manager now makes a call, which is really the subject of the next slide. As the cache manager writes data out to disk to a file, I've said many times, he will inform the file system how far he gets. And the way he does that is by queuing an IRP to the file system, which is IRP MJ information file, and with the subtype file into file information. And in particular, he sets a Boolean flag in there, which can only happen in kernel mode. A user program can't cause this to happen. He sets a Boolean in there, advanced only to true, which says, hey, I'm the lazy writer. I'm giving this file size, but really, it's not the file size. This is the number I'm giving you to tell you how far I've written into the file. So, for example, on NTFS today, we take that information and we go ahead and update the file record in the cache to say, well, this much data has actually correctly arrived out to disk in the file, and therefore, it's okay to let someone read that far out to disk. And this really becomes only important if the system subsequently crashes. If the system keeps running, this valid data length callback stuff is not essential. But C2 does require that even if the system crashes, you can't come up and show somebody uninitialized data, data that used to be on the disk, from some other file. So a file system that actually supports valid data length in its structure will take this lazy writer call back and go ahead and update its valid data length field in its file structures. Okay, the fast I/O overview. I think Gary already talked about this, and you're probably going to get a lot of repetition here. I don't know, it's be one of our favorite topics. I don't know, but it's really used just for these hot paths, and I really only want to talk about read and write, and I mostly have already. It's really a mechanism by which the I/O system calls file systems directly as a procedure call without the overhead of allocating and initializing an IRP. And most importantly, are at least in conjunction with the cache manager, are the fast read and write paths. This is the dispatch table. You can actually see maybe the all of the routines that are supported by fast I/O. This vector starts out with a size field, which says how long the vector is. You should correctly set that to say, how big the vector is you've actually allocated, so that if in a subsequent release of NT we add a few more calls at the end, we can look at your size field and say, aha, this file system hasn't supplied those sizes, so we can implement backwards compatibility in that way. And if there's any of these routines that you don't want to implement, you can just leave a null pointer in those procedure functions, and then you'll get the normal IRP for that request. All of the routines are optional except for the fast read, write, and fast I/O read, fast I/O write, and fast I/O check if possible calls. And those become mandatory if you do cache files. We're really trying to make the read path fast, so we assume that if a file system's smart enough to talk to the cache manager, then it's smart to implement these fast I/O calls. So we don't do any tests to see, well, is the vector long enough? Is there a non-null pointer in the function field? So we just call through there directly. So those three calls become mandatory. And I'm going to talk about the check I/O as possible. Basically, when you're supporting fast I/O, there's a field the FSRTL header that's called is FastIO possible. It has one of three values. And those values are FastIO is not possible, FastIO is possible, or FastIO is questionable. If the field currently contains FastIO is not possible and we get a read request to a cache file, then we don't even attempt to call the cache manager. We just bypass that and give the file system an IRP directly. Whereby if the file system has said FastIO is possible, then we unconditionally call the cache manager to try and service that request directly, and never call the file system at all. We just give the data directly back to the user. And if, you know, I don't know exactly well when you would use not possible, but we have, you know, that some file systems might just insist on seeing every single request because they do auditing or whatever, so we at least give you that possibility. The final value here is we have some more specific examples, and that is if you say FastIO is questionable, then we call one of the other routines in the FastIO vector, which is check if FastIO is possible, and we say, well, we want to read or write range of bytes in the file. Is it okay right now? And then we give the file system the ability to return a Boolean answer to us and say, you know, okay, not okay. And if it's okay, then we proceed and do the FastIO. And if it's not okay, then we generate an IRP and call the file system in the normal manner. And so, for example, one way that we use FastIO is questionable is with file locks. If there's any file locks in the file, then we change the state to FastIO is questionable, and we make the IO system call us by procedure call to do our file lock checks. And then if there's no file lock violation, we say go ahead and just do the read, and otherwise give us the IRP by the lock path, because we may have to reject it or queue it. So this slide is just pointing out that we really do encourage you. I mean, if you want to have a fast file system, we really do encourage you to use FastIO because it's a very, very big win. I think, especially in the case of a read or something, probably the speed of it, the number of instructions to do read by actually generating an IRP is probably several times that of doing a read via the fast path, so it really pays to use the fast path. For all of the functions except read and write, the IO system doesn't provide any exception handlers. So if your file system is like our file system, likes to use exception handling a lot and raise on errors, you cannot do that, however, in the fast support paths and the fast set information paths, because that will cause the system to crash. There's no exception handler on top of you in those fast IO routines. And just remember to always fill in correctly the size of the fast IO dispatch table and always to null out any procedure pointers that you don't support. So I have a few synchronization rules here. And these refer to the routines that I've already discussed. And if there's a routine that isn't present in one of these two slides, that means there is no synchronization rules. I've only listed routines which have synchronization rules. And an E means that, and this is kind of modeled after the use of the executive resources, which are these reader-writer resources, shared access, exclusive access, synchronization primitives that we use in the file systems. So the table's really geared towards that. When you call CC initialize cache map, it's okay to have the file acquired either exclusive or shared. Either way, but you must have acquired one of those two ways. To do uninitialized cache map, you must have it exclusive. And as you see on down the line, CC flush cache, you should either have the file, it's okay to have the file exclusive or to not own it at all, but you better not call that routine with the file acquired shared, because you may get a recursive write to yourself, and you may decide that you wish to have the file exclusive at that time, and that would deadlock. CC0 data requires the file to be exclusive. Now, the cache manager really counts on these rules. If this table says you better have that file exclusive, then indeed the cache manager itself is counting on you for synchronization. He will, without further synchronization, modify some of his structures as well. For the most part, the cache manager is self-synchronizing, but some fields pertaining to your file, he may modify if he's told you have it exclusive. For copy read, shared is enough. For copyright, you should acquire the file exclusive if valid data length is going to be extended. So if you're writing into a new range of the file, and otherwise shared is enough. And similarly, MDL read shared is always enough, but an MDL write shared is enough most of the time, unless you have a write that's going to extend valid data length in the file, and in that case you must have file exclusive. And finally, on an MDL write complete, it's generally a good idea not to own any resources when you call that routine. And so, as an example, you see MDL read complete's not on there because we really have no rules for how you have to call that. I want to point out one more thing on the previous slide, and that is that if you're using the pinning access method, or in fact the mapping and pinning access method, and you call either CC uninitialized cache map or CC purge cache section, then you must not have anything pinned. You must have unpinned everything that you must have called CC unpin BCB on anything that you mapped or pinned prior to this point on that stream. So those routines will deadlock if you have anything pinned and you call them. And that's CC uninitialized cache map and CC purge cache section. Both of those, you better not have anything pinned in the stream when you call those routines, because in fact what the cache manager is going to do is going to go try and unmap everything and start possibly tearing down the section, things like that, and you will block if things pinned. So finally, well, this is a summary slide where I try and summarize everything without sounding too redundant. So I think the Beaver wrote the first sentence here. The cache manager works with file systems to make the best use of available memory. I'll agree with that. The cache manager, I did try and take a different slant at this, and another way to look at the advantage of the particular cache manager that we have in Windows NT is that it increases systems performance in a number of ways. It reduces the overall disk I/O by providing cache hits. And it overlaps disk I/O, so it allows for parallelism in the system, which is nice even on a uniprocessor system, but even more important on a multiprocessor system. It allows for overlap disk I/O by the asynchronous read ahead and the asynchronous write behind that it does. So it increases your performance there. It reduces code paths in the system because it supports the fast I/O path. And finally, it speeds up the file system itself by allowing the file system a convenient way to cache file system metadata. That's it. I'll take questions. Let me just repeat what was suggested earlier. At this time, it would probably be best, so that the people in the poor back room over there can hear us best, if everyone would line up at the microphone to take questions.
I'd like to find out, how does the cache manager deal with sparse files? In other words, reading from a hole or writing into a hole.
I'm sorry, I had a little feedback there. Could you repeat that question?
How does the cache manager deal with sparse files? In other words, reading from a hole or writing into a hole.
The cache manager has no knowledge of sparse files, and if really sparse files end up being a factor of your non-cached I/O path. If somebody tries to read a hole in the file, the cache manager will just go out and touch that page of the file system gets the read, and the file system supports sparseness and says, geez, all or part of this transfer isn't allocated, then he can zero the caller's buffer and return success, and the cache manager never knows about it. And on the right side, well, I guess you tend to write allocate, but again, on the right side, the file system will get the writes, and if it hasn't already allocated the space, then it has to allocate it. Now, since I'm happily working on a sparse enhancement to NTFS right now, I do know some further answers to that question, and that is that there's the ability through the FSRTL header to say that I really always need my file acquired exclusively this hasn't come up earlier in the talk, and that tends to be a good idea for sparse files because you really want the cached writer to acquire the file exclusively, so that if you end up flushing that data, you have a file exclusively, so you can change its allocation. So there is one capability, and that's actually even outside the cache manager as well. But there is a capability in the FSRTL header to say, please always acquire my file exclusive for write operations. Next question.
I don't know about the rest, but I sure would wish that we had some examples on use of cache manager. Do we have that in the that we got, or could we otherwise get somehow?
The answer is yes and yes. The kit that you received has sample code for CDFS, which is admittedly kind of a simple file system. And what else?
Yeah, no.
CDFS? Oh, CDFS and the raw file system. So there is some examples, and CDFS does use the cache manager.
Okay, the CDFS I was aware of, but again, it was said before also that it's only for reads. How about, if you don't want to give us the full HFS, could you at least give us some samples here and there of code that would sort of, get us on the right track for the right side also?
Yeah, I'm not sure the answer to that, Dave.
We understand everybody's desire for example code, and we're actually doing some work to get some sample code to people. We had to balance the desire for sample code with our desire to release things like FastFat that aren't really in a state to release. Believe me, we're not doing you any favors if we give you the FastFat source code. And I think everybody here will nod when I say that. FastFat is fairly convoluted, and a lot of examples that you'd like to see out of FastFat are obscured by optimized code paths and all sorts of things. In the future, and this means 6 months out, 9 months out, like that, we will in fact be working on sample code for file systems that we can release to people. Again, this is very preliminary. This conference, yes, it'd be really great if I could give you all of the HPFS and FastFat and even NTFS source code. I'd be missing a job real quickly if I did that. But we need to stay in touch, and I'll talk a little bit. I have a presentation about what's actually in the kit, and when we get through the cache manager specific piece of the questions here, I'll present that. And then when we do the Q&A at the end, we can talk some more about that if you still have questions about it.
Okay.
So I understand your desire for source, and believe me, I pushed really hard to get you FastFat, even though it's not doing you any big favors. So
no, I think everybody understands that code evolves, and you want to be proud of it first, and all that kind of stuff. Yeah. But as long as you understand the request, and I think it is unanimous,
right,
so,
okay, good. The other thing that I'll point out here is that I don't think any of the NT file systems came online in less than about between 6 months and a year. That's probably not true of FastFat in a very simple form, but in their current form, it took. The minimum probably is a 6 months to a year's worth of time for a reasonable, competent file system. You have. It doesn't sound like it should take that much time, but it's a difficult problem, and we got some really good engineers who spend a lot of time working on this stuff, and we still, as you'll see in David Gould's talk on Wednesday, we still run into deadlocks in the file systems. It's a non-trivial problem. So you have a lot of work to do that you can do usefully with the example code and with the documentation that you have. And we're not going to be standing still while you're doing that work. Presumably we're all just chomping at the bit to just jump up and run out and do a file system, right? So while you're out doing that work, we'll be ginning up sample code, we'll be ginning up more documentation, we'll be getting it out to you so that, as you need more support and you need more help and you need more documentation, it's flowing out from us. Okay.
Next question.
Real kind of in the same tone. Even though this is pretty good, it still puts some of us in a competitive disadvantage when compared with others that have been having access to this for 3 years. It seems that all of these cache manager calls are not documented in your book. It seems what's left are just header files in the diskette. It would be good if you follow up this quickly in weeks, not months, by manual pages for these things.
Oh, okay, that's a point well taken.
I have a couple of questions. One is maintenance of the valid data length mandatory? I had read something that said, some documentation preliminary that said maintenance of valid data length was not mandatory. Is it so? Do I have to inform the cache manager of the valid data length for a file and maintain it by calling cc set file size?
Right. No, you don't have to. The question, I don't know if everyone can, I'm having trouble hearing this microphone myself, so maybe I'll repeat the questions after all. In fact, am I live here? Okay. The question is, does a file system have to worry about this valid data length stuff? And I mean, I would maybe see that in the context, for example, of maybe the file system doesn't goal of being C2 secure. Does it have to worry about that stuff? And the answer is no, and I should have pointed that out. When a file system calls the cache manager to first cache file, it can say that the valid data length of the file is constant max long, which means it's a 7 followed by 15 Fs in a 64-bit quantity. And if you set your valid data length to that size, that effectively instructs the cache manager that, hey, look, I don't care about this valid data length stuff. Don't bother to call me. I'm a simpler file system. VAT file system. I take that back. VAT doesn't do that either. But it is. You can write a file system that doesn't worry about that valid data length stuff.
Is it still working? Okay. Well, the other question is, can I purge the cache of pages even if a user has mapped those pages? If file data has been mapped in, can I get rid of those pages?
That's a really question. Can you purge a file even if a user has it mapped? And the answer is no, you can't. And that's because the memory management structures are all of the linkages flow from virtual addresses down to cache pages, and there's nothing that goes the other way. So in fact, the memory management will reject the cache manager's attempt to purge a file if a user has that file mapped. So indeed, user map files interfere with purging, and if you're using purging for any kind of data coherency, it does interfere with that.
Well, a couple of other questions related to the same thing is, if I cannot purge those pages for a file, how is that handled, for example, by the NT redirector system? If indeed the server wishes, for example, op logs that you haven't spoken about yet, but what happens if somebody else wants to gain a lock on a particular region and a user's mapped the file over here, or the file system interacts with the cache manager, data is mapped in, how do I get rid of those pages? Is there any way at all that I can do that? Second question is maybe something that I'm going to ask. The gentleman describes the memory management subsystem, but is it possible, or is it true that the pages if a user maps a file, or if the file system calls the cache manager to initiate file system caching, certain pages are reserved for those data bytes. If some other user decides to, and it's an executable file, if some other user decides to execute the file at the same time, are the same set of pages used to store data for both those users?
Yeah. Okay, here's a guy that understands a lot of problems here. Let's see, the first question was, if the user mapping a file prevents you from purging pages from the cache, what can you do about it, like in the redirect and supporting op blocks and whatnot? Well, I'm going to tell you theoretically what you can do, and honestly, all of a sudden I forget what our redirector actually does. But you can determine if a user has a file mapped, there's a call, probably either David or Lou will talk about this tomorrow, can file be truncated. And that will, essentially the only reason that routine will ever return false is if a user has the file map. So you can interrogate if a file's mapped, and if it is mapped, then you can decide not to cache it. I mean, our redirector has two modes, and he's able to function entirely without caching. So yeah, indeed, if a user has a file, then you probably don't want to cache the file because you won't be able to honor op blocks. That's a good point, and I mean, it may seem funny, but it's also kind of it's sort of a function of the application. I mean, if that's a funny way to use remote files, then maybe you shouldn't write your application that way. At least the reader can respond in such a way that it can operate correctly with maybe some performance degradation.
Well, it's a little bit more than that. What happens if two users decide to open the file read-write, which is okay because both of them permit shared read-write access. They decide to do the synchronization themselves, and that's all well and good. However, sometime down the road, one of them decides, the third user comes in and maps a portion of the file to read from.
Right.
What does NT as a system accept the fact that stale data can be presented to a user? A, and secondly, can NT live with the fact that once a file is updated on a remote system, on server for example, the user who has the file mapped in comes back, closes the file, comes back in, and may still get stale data. The cache manager has incremented a reference count on the file, and or the memory manager has done the same thing. The file hasn't truly been closed, those pages haven't gone away, and the user says, okay, I close the file, I'm a good citizen, I come back and reopen it.
I see your point. There's definitely some holes, and I encourage you to bring this up tomorrow again when Lou talks. These problems of purging aren't insurmountable. I mean, it's not impossible that, if there was sufficient motivation that the memory management structures could be modified until it is possible for us to support purges in all cases. I mean, I know that's a possibility. So, I mean, go ahead and pepper Lou with these questions tomorrow. But I think you see the answer for right now, and that is that user map files will interfere with the remote file. And your other question about images, no, we don't use same pages because, of course, alignment is different. Image pages don't line up on even page boundaries in the system, and so we again use purge back. If you link a file and immediately run it, then as our testers love to do, then what we do is we will purge the file data from the cache. Again, provided that some user hasn't got the file, but we purge the file data from the cache selectively as pages of the image are being faulty.
So that's a different set of pages completely for the executable as opposed to the
different set of pages, and it absolutely has to be because image pages line up on arbitrary boundaries in the file.
Okay, thank you.
Next question.
You said that the lazy writer writes about a quarter of the dirty pages every second. Is there any way to tell it to be more aggressive? If you want to get it to write a couple megabytes a second data rate, you really have to wait until there's 8 megabytes of dirty pages around.
There's no tuning parameter for accelerating the lazy writer. However, one thing I failed to mention is that in conjunction with this write throttling, as we approach the throttling, I told you the simplest case where he says, gee, everything looks fine, I'm just going to keep going at my slow rate. Because, the lazy writer is pure overhead. I mean, he interferes with your foreground performance. But nonetheless, as you accumulate more and more and more dirty pages, and you start approaching this point where we don't take any more dirty data, and we might start throttling incoming requests, then the cache manager does, in fact, start to get more aggressive. And he, in fact, tries to figure out how quickly you're producing dirty pages, and he tries to accelerate he tries to match your speed. As you approach the throttling point, he says, geez, I'm falling behind. This guy appears to be producing about 1.5 megabytes of data a second. So I'm going to start writing 1.5 megabytes or maybe a little more per second in order to keep up. So he will automatically accelerate his writing under those circumstances, but there's currently no tuning parameter.
Simple follow-up question. Who's the guy to discuss this with offline later? Because I got lots of follow-up.
Because what?
I got lots of follow-up. I'll take it offline. Who's the best person? I would be. Okay. Get you later.
I'll avoid you afterwards.
I was wondering, outside of read-ahead, what kind of blocking factor does the cache system use?
Okay, the block factor for both read-ahead and write-behind is always 64K. Another thing, geez, I ran over as it is, but I did very briefly say that there's a file hint when you open the file that says something about sequential scan, I think, or sequential access. And if you specify that hint, then the cache manager still reads chunks of 64 kilobytes. But the difference is by default, if he senses you're doing sequential access, then more or less every time you enter some new 64K region of the file, he'll try and read the next 64K. So he tries to stay about 64K ahead of you. If you say sequential scan, then he starts queuing off more of the 64K read-ahead requests and try and stay about 3 times that far ahead of you. 196K. He'll try to stay that far ahead of you if you give him that hint. It makes a big difference when, for example, the media player on NT, before they use the sequential scan hint, they might play a complex video sequence and drop. I remember they had one where they, out of 350 frames, they dropped all but 20 or something like that. And then they, coming off CD-ROM, and then they did the sequential scan, and suddenly they dropped a single frame. So it's a big difference.
Yes, I'd like to ask what kind of references does the cache manager hold on the file?
Cache manager
does it hold hard references or soft references? Does it hold a reference per page or a reference per cache client? Or
the reference to the file object. When you tell him you pass in a file object every time you say I want to cache this file, and the first time he sees a new file, he takes that particular file object and references file object itself. So there's a pointer count internally in the system, and so he references that file object itself, and he won't dereference that file object until he's done caching the file. Everyone's called CCN initialized cache map, and he's written out all the dirty data, and everything's all shut down in the file. And as the very last thing, he will dereference that file object. So the file system doesn't have to somehow worry about whether it's going to make a file go away while cache manager is still trying to access it.
Well, okay. What I'm wondering about is there a way to how do you get a last close if the cache manager is still holding references on the file? How does the reference count ever get to 0?
Right. If you flush the whole file and then purge it, flush it if you want. But when you purge the entire file, then and you close, you uninitialize all your file objects that were once cached in that file, then that will cause the file to go away very quickly. It may not happen synchronously, but that will force that file out of the cache and force the cache manager to ultimately dereference his file object.
Yes, but
memory management also has a reference file object, though, and those same steps will cause him to also get lost.
But what kind of external event will cause that to happen? Because, obviously, if I purge the file from within the file system, I know about that, and it cares about references. But see where I'm coming from. We have a file system that does a lot of very complex processing on the last close of a file. We want to be able to trap the last close of a file in order to flash out buffers, metadata, and what have you. And we don't want virtual memory references to count against to prevent that from happening. Okay, there's a catch-22 problem here. Because you're holding references on the file, then the reference count doesn't get to 0. Then we never find out that there are no active references in the form of opens of the file.
So
that's really the
there is one
front of the
capability. I don't know if this meets what you're looking for, but there is a capability to tell. It's that CC initialized cache map call. One of the parameters there is a structure with an event in it. It says, please, I want you to get rid of this file as quickly as you possibly can, and furthermore, I want you to tell me when you've done that.
Okay,
and
so I get
you can specify that event structure, and then turn around and wait on that event, and he'll make it go away as fast as he can, and then tell you when he is done by setting your event. So, yeah.
Wonderful. Thank you.
So you know that you can change your caching strategies based on detecting access patterns to the data, right? And I'm wondering sort of about this your scope of the problem you're trying to solve for the cache manager. So, for example, if you're running, say, 100 sequential batch streams, there's no need to continually read the next 64K view, as opposed to just setting aside one 64K view for one batch stream, right? The previous streams aren't going to be referenced again. So if you had a virtual blocking or logical blocking as opposed to virtual blocking model, you could continue to use same logical again. Similar sorts of comments for B trees and weighting ints blocks or large random data relative to the size of the physical memory, etc. So if I was going to develop a storage manager for NT, I think now to develop my own cache manager. But I wouldn't want to do that. We're going to develop your cache manager in these ways.
So are you asking, let's see, I mean, the cache manager admittedly has some limited algorithms that he applies to detect whether he thinks read-ahead would be beneficial. And he doesn't, for example, other than the sequential scan hint, we don't use any other hints to affect that read-ahead. So are you asking, like, well, I'm just trying to understand.
Okay, let me give you to try to clarify.
I know that there's where's that school where they're doing all that research on I think at Carnegie Mellon they were doing some research where they would feed a lot of hints into the cache manager and trying to figure out what stuff really should be cached, what shouldn't, and influence read-ahead patterns and stuff. And we don't have any activity going on in that direction, if that's sort of what you're talking about.
Here's a real simple one. Sequential access. There's no need to continually map or use sequential views as opposed to reusing the same pages that you just used for the previous view. Do you see my point?
Yes.
And now that's one stream. Now, if you've had 100 of those going at the same time, you're basically walking through cache dirtying it.
Yeah. Now that is an area where we have been putting some thought. So, for example, a copy file API. I mean, it's admittedly, it goes through the cache right now, and it's probably less than optimal. And we've been thinking about ways that we can improve that. I mean, copy file is a perfect example where, you can pretty accurately guess that when you copy these files, there's no reason to believe that they're going to be accessed again real soon. So why should they go sweeping through the whole cache and force other pages out? And so we're looking at ways that we could at least for copy file would be one starting point where we could get a little smarter about that. And we may just decide to make copy file do non-cached I/O and do lots of buffering and stuff like that. That's one approach, but any other ideas there, I suppose we'd be more than willing to hear about. Because we don't have a lot of plans to right now to to get smarter about that. To be honest with you.
Okay.
Any ideas are welcome.
Well, my basic observation is that if you want to get smarter in that area, and if your intention is a cache manager, say general cache manager for storage managers as well, you'll be forced back into logical blocking and away from virtual blocking.
Yeah, we could implement some more file hints too, I suppose, if that's a good way to go. Sort of the opposite of what we do with sequence scanning. Any more questions? Or any more? Gary? Whoops, I saw Gary. I think we. thought Gary was still, okay, so Gary's still here and Dave's here, and any other more general questions?
So questions?
Great.
So,